Wormholes, often described as theoretical bridges between different parts of the universe, are fascinating concepts in theoretical physics. Imagine folding a piece of paper and poking a hole through it, creating a shortcut between two distant points. Wormholes are similar, but instead of folding space, they manipulate the fabric of spacetime itself. Proposed by Albert Einstein's theory of general relativity, wormholes are hypothetical tunnels that could potentially connect distant regions of the universe, even different universes or dimensions. While they captivate the imagination with the possibility of faster-than-light travel and time travel, wormholes remain purely theoretical and have yet to be observed or proven. Nonetheless, scientists continue to explore their properties, examining the intricate interplay of gravity, exotic matter, and the mysteries of the cosmos. Wormholes, the theoretical bridges between different parts of the universe, are captivating concepts in the realm of theoretical physics. Proposed within the framework of Albert Einstein's theory of general relativity, they offer the possibility of shortcuts through spacetime, allowing for travel between distant regions, or even between different universes or dimensions. At their core, wormholes involve the manipulation of the fabric of spacetime itself. To visualize this, imagine folding a piece of paper and poking a hole through it. The fold represents the curvature of spacetime, and the hole represents the wormhole, a tunnel connecting two separate points in spacetime. However, wormholes come with significant challenges and complexities. One major hurdle is the requirement of exotic matter or negative energy density to stabilize the wormhole and prevent its immediate collapse. Exotic matter possesses negative energy and violates the energy conditions we typically observe in our universe. The existence and properties of such matter are still purely speculative and have not been observed. Another obstacle is the tremendous gravitational forces that would be present near a wormhole's entrance and exit points. These forces would be incredibly intense, potentially crushing any object attempting to traverse the wormhole. Navigating these gravitational hazards would require advanced theoretical understanding and technological capabilities beyond our current grasp. Additionally, wormholes raise questions about causality and the possibility of time travel. While it is tempting to envision wormholes as gateways to the past or future, the concept of traversable wormholes capable of facilitating time travel remains highly speculative. Theories attempting to reconcile time travel with causality, such as the Novikov self-consistency principle, suggest that any attempt to alter the past would be self-defeating, leading to a consistent timeline without paradoxes. Despite these challenges and uncertainties, scientists continue to explore the properties and implications of wormholes. They investigate the fundamental nature of spacetime, gravity, and the possibility of interconnecting different regions of the universe. Research in this field encompasses theoretical calculations, numerical simulations, and thought experiments aimed at uncovering the mysteries of wormholes. While wormholes are a captivating concept, it is essential to note that they remain purely theoretical at this point. No observational evidence has confirmed their existence, and numerous technical and theoretical hurdles must be overcome before we can harness their potential. Nonetheless, the study of wormholes not only pushes the boundaries of our understanding but also sparks the imagination with the possibility of traversing vast cosmic distances and unlocking the secrets of the universe. The concept of wormholes can be traced back to the early 20th century when Albert Einstein formulated his theory of general relativity. In 1916, Einstein's theory revolutionized our understanding of gravity by describing it as the curvature of spacetime caused by mass and energy. In the 1930s, physicists Nathan Rosen and Albert Einstein, along with Boris Podolsky, explored the theoretical possibility of bridges connecting distant regions of spacetime. Their work resulted in the Einstein-Rosen bridge, a precursor to what we now refer to as a wormhole. Further developments in the 1960s and 1970s by physicists such as John Wheeler and Kip Thorne expanded our understanding of wormholes and their potential properties. They investigated the mathematical equations of general relativity to study the behavior of wormholes and the conditions under which they might exist. However, it became evident that traversable wormholes, those that could be used for practical purposes, required exotic matter or negative energy to keep them stable. This exotic matter violates known energy conditions and remains purely hypothetical. Since then, wormholes have remained a subject of intense study and speculation within theoretical physics. Scientists continue to explore the mathematical and physical properties of wormholes, the potential implications for spacetime travel, and the fundamental questions they raise about the nature of the universe. Wormholes have not been directly found or observed. They are purely theoretical constructs based on the mathematics of general relativity. The discovery or detection of wormholes poses significant challenges due to their hypothetical nature and the required conditions for their existence. The extreme curvature of spacetime and the need for exotic matter or negative energy density make them elusive and difficult to detect currently. Scientists primarily study wormholes through mathematical models, numerical simulations, and theoretical investigations. Researchers explore the fundamental principles of general relativity and quantum field theory to understand the behavior and implications of wormholes. While the search for observational evidence continues, the existence and nature of wormholes remain open questions in the field of theoretical physics. The formation of wormholes is a topic of ongoing speculation and study within theoretical physics. According to current understanding, wormholes could potentially form through the curvature of spacetime caused by extreme gravitational forces or the dynamics of exotic matter. One possibility is that wormholes could emerge naturally during the evolution of the universe, such as during the early stages of the Big Bang or in the presence of highly concentrated matter like black holes. These scenarios involve the intense warping of spacetime, which could create a bridge-like structure connecting distant regions. Another idea suggests that advanced civilizations or future technology could manipulate spacetime to create artificial wormholes. This concept involves bending spacetime in a controlled manner to form a tunnel or shortcut between 2 points. However, it's important to note that the formation of stable and traversable wormholes is purely speculative. The required conditions, such as negative energy or exotic matter, are still hypothetical and have not been observed or replicated in experiments. Research continues to explore the possibilities and limitations of wormhole formation, but for now, their origin remains a subject of scientific investigation and theoretical exploration. Wormholes, as theoretical constructs, involve several components and concepts within the framework of general relativity. Here are the key components. Spacetime. Spacetime is the fabric of the universe that combines the 3 dimensions of space with the dimension of time. Wormholes manipulate the curvature of spacetime to create shortcuts or bridges. Einstein's field equations. These are the mathematical equations formulated by Albert Einstein as part of his theory of general relativity. They describe the relationship between the curvature of spacetime and the distribution of matter and energy. Exotic matter. The existence of stable and traversable wormholes often requires the presence of exotic matter or negative energy density. Exotic matter possesses negative energy and violates conventional energy conditions, which are typically observed in our universe. However, exotic matter remains purely hypothetical and has not been observed in nature. Throat or passage. A wormhole consists of a throat or passage that connects 2 separate regions of spacetime. This passage can be visualized as a tunnel or bridge, allowing travel between distant points. Einstein-Rosen bridge. The Einstein-Rosen bridge is an early theoretical construct, proposed by Nathan Rosen and Albert Einstein, that forms the basis of the concept of wormholes. It describes a mathematical solution in general relativity representing a bridge connecting 2 different regions of spacetime. Stability and traversability. Wormholes need to be stable and traversable for practical use. Stabilization typically requires the presence of exotic matter with specific properties to counteract the collapse of the wormhole under intense gravitational forces. Traversability refers to the possibility of safely traveling through the wormhole without encountering extreme tidal forces or other dangers. It's important to note that while these components provide a conceptual framework for understanding wormholes, their actual existence and properties are still speculative and subject to ongoing research and investigation within the realm of theoretical physics. Within the theoretical framework of wormholes, several types are commonly discussed. Here are a few notable types. Schwarzschild wormholes. These are hypothetical wormholes that are based on the Schwarzschild solution in general relativity. They are often depicted as spherical or donut-shaped and are formed from the gravitational collapse of a massive object, such as a star or a black hole. However, traversable Schwarzschild wormholes would require the presence of exotic matter or negative energy. Morris-Thorne wormholes. Proposed by physicists Michael Morris and Kip Thorne, Morris-Thorne wormholes are theoretical constructs that attempt to address the issue of stability and traversability. They introduce the concept of a throat within the wormhole, where the geometry allows for safer passage without encountering extreme gravitational forces. Ellis wormholes. Named after physicist George F. R. Ellis. Ellis wormholes are mathematical solutions in general relativity that describe bridges between different universes or disconnected regions of spacetime. They provide a theoretical framework for exploring the possibility of interconnecting different realms. Quantum wormholes. Quantum wormholes are speculative in nature and involve the application of quantum mechanics to the study of wormholes. These types of wormholes are often discussed in the context of quantum entanglement and the potential for quantum teleportation, where information is instantaneously transmitted through the wormhole. It is important to note that these classifications represent different theoretical approaches to wormholes and are subject to ongoing research and debate within the scientific community. The existence and properties of these various types of wormholes are still purely hypothetical and have yet to be observed or confirmed. Here are a few notable research papers related to wormholes. Traversable Wormholes in 4 Dimensions, by Matt Visser, 1995. This seminal paper explores the theoretical aspects of traversable wormholes and discusses the necessary conditions, such as exotic matter and negative energy, for their existence. Quantum Wormholes, by Juan Maldacena and Leonard Susskind, 2013. This paper investigates the connection between entanglement and wormholes, exploring the possibility that entangled particles may be linked by quantum wormholes. Wormholes, Quantum Information, and Holography, by Netta Engelhardt, Gary T. Horowitz, and Jorge E. Santos, 2019. This research examines the potential role of wormholes in quantum information theory and the holographic principle, which relates gravitational systems to lower-dimensional descriptions. Traversable Wormholes via a Double Trace Deformation, by Ping Gao, Daniel Lewis Jaffaris, and Aaron C. Wall, 2017. This study proposes a mechanism to construct traversable wormholes using a double trace deformation in quantum field theory, providing insights into the quantum nature of wormholes. These papers represent only a small sample of the research conducted on wormholes. To explore the latest developments, I recommend consulting scientific journals, preprint archives, and academic databases to access the most recent and comprehensive research in the field of theoretical physics. Wormholes remain purely theoretical constructs within the framework of general relativity. However, I can provide some indirect points that researchers have considered in support of the potential existence of wormholes. Mathematical consistency. Wormholes are mathematically consistent within the equations of general relativity. Theoretical physicists have developed mathematical models and solutions that describe wormholes, exploring their properties and behavior based on the principles of spacetime curvature. Solutions in general relativity. Certain mathematical solutions in general relativity, such as the Einstein-Rosen bridge and Morris-Thorne wormhole solutions, suggest the possibility of wormhole-like structures under specific conditions. These solutions demonstrate that wormholes could exist within the framework of the theory. Theoretical extensions. Some theoretical extensions of general relativity, such as certain aspects of quantum gravity or string theory, suggest the existence of wormholes or related phenomena. These extensions provide additional mathematical frameworks where wormholes may potentially play a role. Cosmic inflation and early universe. Some researchers have explored the role of wormholes in the context of cosmic inflation and the early universe. They investigate whether wormholes could have influenced the rapid expansion of the universe or played a role in the formation of large-scale structures. It's important to note that these points do not constitute definitive proof of the existence of wormholes. Wormholes remain speculative and their practical realization faces significant challenges, including the requirement for exotic matter, stability issues, and the lack of empirical evidence. Further scientific exploration and advances are necessary to gain a better understanding of the nature and possible existence of wormholes. Here are some key facts about wormholes. Theoretical bridges. Wormholes are theoretical constructs that propose the existence of bridges or tunnels connecting different regions of spacetime, potentially allowing for shortcuts between distant locations, universes, or dimensions. General relativity. The concept of wormholes arises from the mathematics of general relativity, Albert Einstein's theory of gravity, which describes how matter and energy curve the fabric of spacetime. Exotic matter. Stable wormholes often require exotic matter or negative energy density to counteract gravitational forces and prevent their collapse. Exotic matter possesses negative energy and violates conventional energy conditions observed in our universe. Stability and traversability. Traversable wormholes, those that allow safe passage through them, present significant challenges. The extreme gravitational forces near the wormhole's entrance and while wormholes are intriguing theoretical constructs, they also face several challenges and potential faults that limit their practical realization. Exotic matter. The stability and existence of traversable wormholes often rely on the presence of exotic matter or negative energy, which violates the known energy conditions observed in our universe. Exotic matter with negative energy density has not been observed or replicated in experiments, and its properties remain purely hypothetical. Energy requirements. The creation and maintenance of wormholes would likely require enormous amounts of energy, far beyond what is currently achievable or understood. The energy needed to stabilize and prevent the collapse of a wormhole remains a significant challenge. Unknown physics. Wormholes exist at the intersection of general relativity and quantum field theory, both of which have their own unresolved questions and inconsistencies. The lack of a complete theory of quantum gravity makes it difficult to fully understand the behavior of wormholes on a fundamental level. Information paradox. The presence of wormholes raises questions related to the preservation of information. The information paradox, associated with black holes, also extends to wormholes. The fate of information entering a wormhole and the potential violation of fundamental principles, such as causality, remain open questions. Macroscopic instabilities. Wormholes are susceptible to macroscopic instabilities, such as fluctuations in energy density or the formation of quantum foam. These instabilities could render wormholes either transient or non-traversable. It's important to recognize that these faults do not conclusively disprove the existence of wormholes, but rather highlight the significant challenges and unresolved issues associated with their theoretical framework. Further research and breakthroughs in fundamental physics are necessary to fully understand the nature and feasibility of wormholes. This video has delved into the captivating subject of wormholes, theoretical bridges between different parts of the universe. We have covered their history, formation, components, types, and ongoing research. Wormholes remain theoretical constructs within the framework of general relativity, but they spark our curiosity and expand our understanding of the cosmos. Thank you everyone for watching. Subscribe for more informative videos.